Okay. Oh, yes, that's the right first word. Corresponding.
Correspond to
This is pretty good. I mean, you're not that far off. I'm hearing corresponding pieces. It's a word that's similar to pieces, but it's not pieces. Parts. And there is the word of in there. So it's corresponding parts of congruent triangles are congruent. Yes, that's it. Okay. So let me actually switch to blue. I think it shows up better. Well, would you do me a favor and shut that light off? I think it shows up better. Okay, so thank you. 4-3. We are going to do, I'm going to call this the acronym Cpctc. It's quite fun to say. Yeah, so let's explain what this means. Corresponding parts of congruent triangles are congruent. So that is a mouthful. So we have come up with this this acronym to more succinctly say all that. And this is recognized everywhere. This isn't just like a Tantasco thing. Like you'll see it in textbooks, and so other people will know what you mean when you say Cpctc if they've taken geometry. If they haven't, they're going to look at you like I don't know what you mean. But there you have it. So Cpctc. Now, what is it actually saying? So what this means is, let's just say I have two triangles and I'm able to prove that they are congruent using any one of my 5 methods. It doesn't matter. So let's just say, to make it easy, let's just say we did side, side, side. So if I already knew that these two triangles were congruent by side, 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 what I can now say is, I can remember there's really 6 things that you know are, in order to prove 2 figures are congruent, aren't you supposed to check all the sides and all the angles? So we have the 3 sides. So what Cpctc lets me do is now say, hey, if the triangles are congruent, so are all those other pieces that we haven't talked about yet. So I could now say, if I wanted to prove that angle C was congruent to angle F, I can do that now because I know that the triangles are congruent. And if triangles are congruent, their corresponding parts will also be congruent. So corresponding parts of congruent triangles are congruent. So now I could say, therefore, angle C has to be congruent to angle F. Angle B would have to match up with angle E. And so on, right? All of the other pieces I get for free. So if triangle ABC is congruent to triangle DEF, then I can say, or like, let me add by side, side, side. I can also say angle A is congruent to angle D, angle B to angle E, and angle C to F. So I get all of those other bits of information. So prove them congruent any way you want, and then just go one step further and we get to use the CPCTC business. So I think this is a great time for us to try it in a proof. So let me draw you one. Let's do something like this. Thank you. Let's say I gave you, what do I want to give you here? Okay. So let's try this one. See if we can figure this out. I think we can. So look at what I'm trying to prove this time. I'm not just trying to get the two triangles congruent. I'm trying to get B and D the same. Well, gosh, those are corresponding parts of these two triangles. So my goal is now I still want to get the triangles congruent, because once I have that, now I can say angle B is congruent to angle B. So it's really just going one step further than we went yesterday. All right, so let's try it. Let me get my statements, my reasons. I know my first statement is going to be all that given. I'm also going to mark it in the diagram. So I know what I've already proved and so I know that BC is congruent to AD, so I get to mark that. And I also know that they're parallel. By the way, one other common mistake that I see students making with proofs is that they'll mark something in the diagram and then never write it in here. If it's not written in here, I can't do anything for you. So just because you mark AC congruent to itself in the diagram, I mean, that's great, but you have to tell me that down below. If you don't say it there, there's nothing I can do. You follow me? So what would I write to do? I want to do this, right? I want to mark AC. So Isabella, how do you write that? Yeah. So AC is congruent to AC, and what's the reason? Yes, that's when we use that reflexive property. And hopefully now you see how important it is. Because without that piece, I would be missing a side. But now I have two sides. All right, that's cool. So I have two sides so far. What can I do from here? Aiden?
So angle CAD
angle BCA. What was your first angle?
CAD.
Oh, CAD, yeah. So angle CAD, we could say is congruent to BCA. Thank you. So I'm going to mark it in my diagram. So that's this one congruent to this one. And how did you know that that was true? How do you know? Yeah, what let you say that? Yes. That's it. The parallel lines are the thing that gave me my congruent alternate interior angles. So you need all of those pieces. You need to tell me that because I have parallel lines, I can now say alternate interior angles are congruent. Now, I think we have enough to say that the two triangles are congruent, don't we? By which method? Julia? I'm sorry. It would be side angle side. Now listen, This part's up to you. You have to write that congruency statement correctly. So let's all name the first triangle as ABC, just so we match. So if you do ABC, fill in how you have to name the second triangle. It matters. You're gonna lose points if you get it wrong, so be careful. Aiden, you have it?
triangle.
Hold on, let me see. So ABC. CDA, I believe, yeah, CDA it should be. Triangle CDA. Again, use the markings to help you. Use the markings. So in triangle ABC, for example, you see that C has an arc on it. So you know wherever C appears in the first triangle, that's where A is going to have to appear in the second triangle. So I have C on the end, I have to have A on the end. You can also look at, D and B, it's pretty obvious that they match up, but if you look at D, D is made up of two sides that have one slash on it and no slashes. B is the same thing, one slash and no slash. So I know B and D are going to match up. And then I have that A and C again. Okay, and then my reason we said was side angle sine. So you literally just write SAS, that's all I need. You don't have to write postulate there, whatever. I don't care about that. But that's not what I was trying to prove, right? My end goal is to prove that B and D are the same. But can't I say that now? Once you have proven that the two triangles are congruent, all of their pieces are congruent too. So I can literally now just say, all right, angle B is now congruent to angle D. And my reason is our cute little acronym Cpctc. You don't have to write all that stuff out. You just have to write the letters. See, it's not so bad. You would have done the exact same thing. Let's say instead of trying to prove angle B to congruent to angle D, if I had said, hey, prove to me that side AB is congruent to side CD. Same thing, get the triangles congruent, and then that last piece, those are still pieces of a triangle. All three sides and all three angles you get once you have the two triangles congruent. Isn't that neat? I knew you'd like that. Okay. Questions about Cpctc? Yes.
What's the reason for the wait, why can't you say that?
So once you
Okay.
get the triangles congruent to each other, now any of these, so remember when we talked about, when we first learned about a congruent statement? And I said, even without a picture, you can just tell from here that angle A and angle C match, angle B and angle D match, angle C and angle A match. And then we also said side AB matches with side CD. Any of those pieces, you now get to say for free because of Cpctc. Corresponding parts of congruent triangles are congruent. Yes. So again, if I'm grading this, I'm starting at the bottom. I'm like, okay, cool, they did that. Yep. So I checked, did you do this congruent statement right? Is in the right order. Remember, you can name the first triangle however you want. So you just have to name the second one to match. So I'm just checking, okay, do they have A and C in the same spot? B and D in the same spot? And then I say, okay, they use side angle side. So then I'm looking up here, I'm like, oh, okay, cool. There's an angle, there's a side, and yep, there was another side in the given. So now I know, okay, they at least did two sides and an angle, and then I just make sure that they're the right ones. Make sense? Okay, any other questions on Cpctc? Cpctc. The last thing we need to talk about today is isosceles triangles. They're so cool. Wait till you find out all the fun things about isosceles triangles. You never knew there was so much to them. So first of all, someone remind me, what even is an isosceles triangle? What does it have? Yes, two sides are congruent. So when you look at an isosceles triangle,
It still feels like there
Oh, no, this is 4, 4 now. Okay, so isosceles triangle, check this out. So two sides are going to be congruent. Yes, naturally. Boop, ba-doop, ba-doop. Those two sides that are marked congruent, we refer to those as legs. So this thing is a leg and this thing is a leg. The other side that's not congruent, I don't want to say bottom because this, right? Could you take this triangle, turn it upside down? So it doesn't necessarily mean bottom, but the one that's not congruent, we call that the base. And now, just like any other triangle, it has 3 angles, but now we have special names for these angles. Where those two congruent sides meet, this angle right here is called a vertex angle. And I don't know if you remember me talking about this a while ago, but do you remember what I said about the angles in an isosceles triangle? Does anyone remember? We spoke about it briefly. You have two sides the same, Aiden? Yes. In any triangle, however many sides you have the same is how many angles you're going to have the same. So if I have two sides the same, that means two angles are going to be the same. And those will be the two ones down here. They are called the base angles, right? Because they go along the base. And they are always equal to each other. Oh, I hate how those touch. Let me see if I can fix that. It's going to bother me. Oh, yeah, there we go. So these two are referred to as the base angles. Sorry, my phone is dinging. I thought it was on silent. So in fact, we get our first theorem for isosceles triangles. It's called the base angle theorem. And it states if two angles in a triangle are congruent, then the opposite sides are congruent. Oh my gosh, sorry, I messed that up. I gave you the converse first. Change the word angles to two sides. The two sides in a triangle are congruent, then the opposite angles are congruent. I'm so sorry. I was looking at my notes and I copied from the wrong spot. So if two sides in a triangle are congruent, then opposite angles are congruent. And then, as I mentioned, we're going to have the converse to this. So here is the base angle theorem converse. Do you remember what a converse is? When you switch the hypothesis and conclusion. So here we're going to say what I wrote the first time. If two angles in a triangle are congruent, then the two sides, the two opposite sides are congruent. Okay, one more theorem on the isosceles triangles. It doesn't have a cute little name, unfortunately. It just states the angle bisector of the vertex angle of an isosceles triangle is perpendicular to the base at its midpoint. What? That can't be true. Oh, it is. We're gonna see how it is in just a second. We have a nice name for that. We call that a perpendicular bisector. So that segment would be referred to as a perpendicular bisector, which is a nice name because the name literally tells you what it does. It's perpendicular and it's bisecting. So let's briefly explore this. How in the world could this be true? So I'm going to start off with an isosceles triangle. There we go. Then they're telling me that I am going to bisect the vertex angle. So if I come in here and I go ahead and I bisect that vertex angle. So remember, the vertex angle is where the two congruent sides meet. So if we bisect this angle, remember what that means. It means that these two angles are now congruent. They mean to tell me that you have enough information now to say that these things are perpendicular and that it's a midpoint? How would they know that? We can't go around assuming 90-degree angles unless we can prove it to be true. Oh, and we can. Check this out. Just think of these as two separate triangles. See them? Don't think about the whole big triangle. We have a left triangle and a right triangle. Don't they share a side down the middle? You bet they do. Don't you have enough to say that those two triangles are congruent now? Using what method? Carson?
Side angle side.
Side angle side, right? Now, go further. If you use Cpctc, wouldn't it be true that angles 1 and 2, let's say, would be congruent to each other, right? I have congruent triangles, so all their corresponding parts are going to be congruent. So angles 1 and 2 are going to be congruent. I think that proves that they're 90-degree angles. How? If 1 and 2 are equal to each other, how does that mean that they're 90, Isabella? Yes, that's a linear pair, right? They together make 180. So they're equal. That's 90 and 90. It is perpendicular. So that segment that we drew, the angle bisector, I have proven is now perpendicular to the base. But they also go further. They say at its midpoint. Yeah, because I know this. How would I know this piece is equal to this piece? Carson? Cpctc again. You get another little tidbit. Now yeah, that's absolutely true. So if you have an angle bisector that's bisecting the vertex angle of an isosceles triangle, it's perpendicular to the base at its midpoint. That's so cool. I know. Okay, one last little tidbit. We did kind of already talk about it, but we'll just make it official and stick it in our notes. So we have a corollary from all of this. Corollary. So if we have an isosceles triangle, if two sides are the same, then two angles are the same. Doesn't that mean in an equilateral triangle, if I have three sides the same, won't I have three angles the same? And vice versa. So basically, all we need to say is that an equilateral triangle is equiangular. Equiangular and vice versa. We've already kind of talked about that. But now it's official. Okay, I have a really good problem for us to try. Let's see if you can make sense of this thing. I'm gonna try and draw it accurately. This a bit longer. Okay, watch this. I would love for you to find me angle X. I'm literally not going to give you any numbers. See if you can find angle X using the things that we talked about today or old information that you know. Oh my gosh. Do I know the answer? I don't have it written down, so let me do it somewhere else where you can't see. Okay, I have my answer. You have it too? Okay, hold on to it. I'm gonna give everybody maybe one more minute. See if you can arrive. It's a nice number, I'll tell you that. I'm gonna give you one more problem to do after this, so. I'm gonna sneak that one in right here. Okay, so do I have some answers for this first one? I know I have one from Aiden. Anybody else have an answer? Okay. All right, Aiden, what's your answer? 150. Carson, is that your answer?
No, I'm not one.
145, Julia?
I don't want
150? What'd you get?
135.
135? Any other answers?
I don't want 50.
150? There is a correct answer out there. Let's see which one it is. All right, so I have no numbers here, but I do notice, okay, cool. I have some, I have a couple of triangles here. Here is an equilateral triangle, right? All three sides are marked the same. We've talked about this. If all three sides are the same, then all three angles are the same, which means they all have to measure 60. So all three of these angles inside the equilateral triangle are 60. That at least gives me somewhere to start. And then I'm looking around and I'm like, okay. Oh, look at this. Aren't these two a linear pair? Right? Don't these two have to add up to be 180? Yeah, so that's 60. Now I know this one's 120. Ooh, that's interesting. And now, ladies and gentlemen, think about what we learned today about isosceles triangles. Don't I have, if I cover this one up, don't I have an isosceles triangle right here? And the angle where the two sides meet is the vertex angle. And what do you know about the other two angles? Yes, the base angles are always going to be equal to each other. That's a big deal. So these two base angles are going to be equal. You can find out what they are. If they all have to add up to be 180 and the top one's 120, that leaves behind 60. And I got to split it evenly between the two of them. Doesn't that mean it's got to be 30 and 30? Right? Yes. You're 30 and you're 30. And now that I know you're 30, I could find the angle on the outside 150. Or you could have done, it is an exterior angle, so it's equal to the sum of its two remote interiors. No matter how you slice it, you get 150. Yes. I gave you one more fun problem to try. That's an x plus 6. It's kind of weird. It's just an x. Oh, golly. Try that one if you haven't already. I'm going to see what I want. I think I'm going to change it from what I normally do. Yes. Okay. All right. Anybody have an answer for this? Aiden, what'd you get?
X equals 3 or negative 2 and y equals 1.
I almost agree with you. I think there's, you would have two answers for y, wouldn't you? You have two answers for x, right? So if it's 3 or negative 2, so then you would just give me the whatever else y could be. But yes, that's basically it. So, what? All right, so I'm looking here and I'm like, oh, okay, yes, I noticed I have two variables, but look, I have two sides marked the same. It's always the angles. I almost like to think of the little congruence marks as arrows pointing to the two angles that are going to be the same. This angle and this angle, those are the base angles. Those two are equal to each other. So I can literally write x squared equals x plus 6. If I can solve for x, then I can go back and solve for y. So I actually don't have to solve a system here. Could you solve a system? Maybe. I don't even know. I mean, yeah, all three would have to be 180, but I don't know what your second equation is.
Yeah, I was trying to do this just like
Yeah, you'd end up here anyway. So, but this I can solve. So let's set it equal to 0 minus x minus 6 equals 0. Let's factor that. That would factor into x minus 3 and x plus 2, which means that my answers for x are either positive 3 or a negative 2. Now, yes, we do need to stop and ask ourselves, can I even have -2? You can this time, because when you plug it back in, -2 squared is just 4, and -2 plus 6 is still 4. Nobody goes negative. So they are both legitimate answers for X. So if X is -2, let's just start with that because we know the answers. If that's 4 and that's 4, that means that adds up to be 8. Take that away from 180. Wouldn't that mean angle Y has to be 172 degrees? Right? So Y could be 172 if X is -2. But if X is 3, let's see what the other answer would be. That'd be 9 and 9. So that's 18 off of 180 is 162. Yeah, so it either could have been 162 or 172. Oh, isn't this fun? Don't you love isosceles triangles? I knew you would. I knew it. And I knew you'd love CPCTC. Okay, here is your homework. That's an 8, if you can't tell.